A particular case of superposition of waves is that where a traveling wave is reflected off of a surface, say a mirror. For the incoming wave, let's say traveling to the left, we write the oscillating electric field as E naught sine of omega t plus kx. For the reflected wave traveling to the left, we write E naught sine of omega t minus kx minus phi, where phi accounts for any phase shift occurring at reflection. As a matter of fact, for an electromagnetic wave reflected off of a plane mirror, that phase shift will be pi. Imagine the reflection takes place when the electric field is zero. Then there is a change in the direction accounted for with this negative sign in kx. But if there was no phase shift, this would mean that the amplitude of the electric field would follow the steps of the incoming wave. But it doesn't. The amplitude of the E field actually goes opposite to the incoming. So that's why the pi phase shift. If we have two waves interfering, this can be an optical cavity made of two mirrors. This is what actually happens in lasers. Lasers are a resonant cavity with two mirrors. Then the net electric field is the sum of both electric fields. If we make use of the trigonometric identity, then we can rewrite the net electric field as 2 E naught cosine of kx plus phi halves times sine of omega t minus phi halves. This, as you might remember from your introductory course in physics, is a standing wave. Because of the pi phase shift at the mirror, phi over 2 is pi over 2, so the cosine becomes a sine and the sine becomes a cosine as this, because of the relation of the phase in both the cosine and the sine, in this equation is not actually dependent on what the actual phase shift is, so long as the amplitudes are the same. Look that for a given time t, the amplitude of the E field along the x-axis is a sine wave. For a given position, the amplitude of the E field oscillates as a cosine wave. This can be thought as a wave that evolves in time with an amplitude that depends on the position. That is, the maximum amplitude of the electric field will depend on the position. There will be positions for which the amplitude is always zero. For those positions for which the sine of kx is zero, which happens to be for 0, pi, 2 pi, 3 pi. For those positions, there will be no electric field. Those will always be nodes of the waves. Because k is 2 pi x over lambda, those positions are multiples of half a wavelength. On the other hand, there are moments in time for which the amplitudes will be maximum, the maximum possible at each x position. That will happen when the cosine of omega t is maximum, which happens for omega t 0, pi, 2 pi, 3 pi, and so on. Because omega is 2 pi the frequency, those times are multiples of half a period. Let's talk a little bit about lasers, because this description is very relevant for them. In a laser, you have a small resonant cavity made of two mirrors facing each other, and a gain medium between the mirrors. The gain medium is the one that is going to use the standing wave to stimulate the emission of light. But the gain medium will only be able to emit some very specific frequencies. To amplify the signal, you want those frequencies to fit in the cavity. So if you have a cavity of separation d, that separation has to be an integer multiple of half the wavelength. So the allowed wavelengths are 2d over m, which gives us allowed frequencies c over lambda, which is mc over 2d. For example, let's consider a Heine laser, like the one in the James Bond Goldfinger movie. Heine stands for helium and neon as gain medium. The Heine atoms will emit photons in the range of wavelengths between 632.800 nanometers and 632.802 nanometers. If we have a cavity of 30 centimeters, well, this size is not going to be Goldfinger's, but a typical student's laboratory laser. That cavity hosts m full half wavelengths given by 948,166. This gain medium is going to generate a wide range of frequencies related to the range of wavelengths. To calculate the range of frequencies, (1.50 gigahertz) is the range. We will have frequency equally separated, and the separation is given by nu m plus 1 minus nu m. (500 megahertz) is the frequency separation between allowed frequencies. But from all these frequencies, from all the frequencies emitted by the gain medium, not all are going to be allowed in the resonant cavity, only those that match the standing wave condition. To those we'll call the modes of the laser. So, the number of standing waves modes allowed are n equal to delta nu of the gain medium over the distance between two consecutive frequencies. Which gives us 3 modes. This laser will be a multi-mode laser that emits 3 modes, which are the only ones that form standing waves in that cavity. These modes will be separated by those 500 megahertz. This is not a single mode laser that emits just one single frequency. If you want a single mode laser, you need to work with this parameter to only allow for one frequency. Of course, there is more to this, as the temperature affects the gain medium and will change slightly the frequencies emitted. If the laser is working for a while, its temperature will increase. This can also affect the dimensions of the cavity. But we'll talk more about this in the chapter dedicated to lasers. In the meantime, may science be with you.